number 1. And that's a huge machine. The problem number 2, for 2, we only prove so for 2 we proved using AC, proved using ACF monotonicity function C11 locally. So this is what we have been doing. Actually, 2 can be seen, can be generalized further to Laplacian of U is FRX and U, or more general operator for Laplacian. Even the first one can be done. For 2, so this is basically a semilinear problem, and F has some discontinuity of first order, second order, etc. in the variable U. So for 2, there are open problems. I would say most of the questions you want to ask, they are not answered. So for 2, you want to do regularity of the boundary. It's completely, well, not completely, but in special cases, but then you can actually work with. Still, you have to assume F prime is non-negative. It's a monotone increasing. So nobody has really taken them up and worked with them. I have a small paper. It's more like a discussion paper. It's called narrative. The narrative approach to a free boundary or something. In that paper, I have put several questions, open questions in this regard. So those of you who would be interested can look at that. If I remember the title correctly, it's a paper by myself. A narrative approach to I don't know what. To semilinear problems or free boundary problems, something like that. Okay, so that paper actually contains.
Which year is it?
It's 4 years ago, 5 years ago. The narrative approach. Do you find it? Search narrative approach with my last name. You will find it. The semilinear problems are free boundary. I don't remember exactly. It's on my research page, my webpage. That contains a lot of questions that you can really work with. If you would be interested, you can look at that. I'm not sure if somebody else picked it up, but that's there anyway. Okay. So for you, those of you who would be interested, maybe make some research around it. Maybe this is a good direction to continue. All right. So let me now say what you have been doing. So we focus mostly on this type of problem. So another problem you want to look at is system case. So 3, system case. So now, instead of one function, you might have several functions, and you want to work with that. And there has been several ways of generalizing this to system case, but the one that we think seems to be reasonable, at least reasonably hard, in the sense that it doesn't become trivial, is the following. That you have a vector u, so instead of the function, scalar function, you have a vector. So Laplacian of this vector, it means that you take the Laplacian of each component, is going to be the vector itself divided by the length of it. And of course, times characteristic function when the vector is not zero. This is the system case. So the vector u is u1, un, and we're working Rn. And this is comes from the Euler equation, Euler-Lagrange equation, comes from minimizing the functional, let's say it will be 1 again, gradient of the vector u to power 2 plus, I guess, 2 or something. Of u. So if you minimize this functional, then you're going to get such an equation. This is quite recent. I think it's a few years back. And we're going to study this. And there are interesting outcomes. You see all the devices here, not all of them will work. You realize that Laplacian of u vector, so Laplacian of u1, so for instance, Laplacian of u1 or uj, so Laplacian of uj is uj divided by the length of the vector u. So it's far from being elementary. It's not like 1. It's not like the function f of x. It's highly nonlinear, so it depends on the function itself. And let us look at a few situations here.
Also, this is cycling. No.
I allow you to change sign. So the components can be negative and positive. Of course, you can also ask them only to be non-negative. As one way. But let's look at this function. So if it's one component, if scalar, that's f is 1, only one component. So what do you get? You get Laplacian of u1, only one component, is u1 divided by u1 length. And what is this? This is the sine of u1. And this is what? This is exactly characteristic function. When u is positive, u1 is positive, this is going to be 1, and then it's going to be minus characteristic function u1 is negative. And it's going to be minus 1 when u1 is negative. So you see, you get a problem that's very close to what I started with. That's not a problem. And here you see that it's a two-phase problem. So more generally, we have a two-phase problem. Which is Laplacian of a function u, it's not a vector, is lambda plus characteristic function, this can depend on x, u is positive, minus lambda minus characteristic function of u is negative. And this comes from minimizing which arises from minimizing the following functional. If you minimize this functional, this is what you're going to get. And now you already realize that this is a little bit This is the right hand side, f. So this guy is f. So if we put f of x u is lambda plus characteristic u is positive, minus lambda minus characteristic u is negative, then one can actually prove that the Laplacian of any directional derivative of u is going to be f direction e, directional derivative of f, plus f derivative in u, and then lambda plus lambda minus, and then restricted to hn minus 1, something like this. And then you have a little bit more here, maybe. Plus, yeah, we have a little bit more. You have the gradient coming in. You have directional derivative of u, something like this coming in. So if you take this guy, take the plus minus part, you're going to get this plus minus part in hn minus 1 Hausdorff measure, and you see that this is not negative. If you assume this, so this is an assumption you have to make. Assumption. So generally we assume that this is non-negative. So lambda plus lambda minus has to be non-negative. If that is non-negative, then this is going to be non-negative. And then this is going to be, let's say, Lipschitz that's going to be bounded from minus some constant. If f is Lipschitz in the x variable. So this means that the whole thing is going to be larger than minus 0. And once you have this, then this is actually ready for applying the monotonic formula called Caparo-Brito. Because in that we assume non-negativity, but we can actually go down with a little bit negative, but not minus infinity. We can still work it out. Versions of that came much later. So that will actually result. So this together with monotonicity formula, I'm going to go back to the system. So this gives plus monotonicity formula is the improved version by Caffarelli, Gerson, Cheney, some other people. Gives u is C11. So for the two-phase problems, you actually also get C11 regularity. And then after that, people have gone further and prove a lot of regularity theory for the free boundary itself. So what happens is that the free boundary now is a little bit different. So here u is positive, here u is 0, and here u is negative. And the free boundary is now, here is like the classical obstacle problem, here is the classical obstacle problem, but here is a little bit different. So what one can prove is that the free boundary can split into two pieces. One piece is this one, the next piece is this one. Each one is C1 graph, locally. So we call them branch points. So this is a branch point with branches. The branch point, the free boundary is always C1 graph. It is never C1 alpha, but it's always C1. You can actually prove it's not C1 d. Then some trouble can come through. So you don't get them. In general, of course. In some cases you get them, but in general you can prove there are examples when you don't get C1 d. So these are the directions that people have been working on with two phases. And the system I started with, that system in specific case brings down to this. But if you assume non-negativity, then the system goes down to the obstacle problem. So if you assume non-negativity, the system for m is 1 is not the system anymore, and U, let's say 1 non-negative, it gives that you get this. The sign of U1 is just characteristic function of U is positive. That's exactly what it is. It's 1 and 0. So we get the problem back. So a few years ago, we studied that problem again for the system and for the system case, very generally and assuming a little bit flatness. We didn't assume non-negativity, but we assumed a little bit flatness as the free boundary is good enough. Let's say it's in between two parallel planes, then automatically, we proved it. Okay, we assume that the free boundary is flat plus that the function u, vector u is 0. We need that. Then, of course, you're away from the two phase. Automatically, you're away from that. And then we showed that the free boundary actually going to be C1 alpha locally at such points. So these are things that we have been doing for vectorial cases. But there are still a lot of open problems here to study. So this is one type of problems we have been working on. There is another problem, system case. So let me mention another problem, Bernoulli problem. One further thing maybe that I mentioned is that we have been looking to the following problem as well. Find is logarithm of u. Let's say u is less than 1 here. And then characteristic function. Let's say u is less than 1, so we have, doesn't really matter, but u is non-negative. U is larger than or equal to 0. Yeah. So otherwise we don't have a meaning. You see, this is the obstacle problem with log singularities. This problem also appears, I guess. Yeah. But anyway, some people were asking this question when we started studying it, and then you get C11 for solutions. Regularity of the free boundary, we don't know at this moment. Not much is known. So these are all things that are completely open, and we can of course go further with two phases, etc. I guess in the near future, some people will pick it up and work on that. Okay, so then I was going to mention about Bernoulli problem. Bernoulli. For the Bernoulli problem, you have a little bit different. So what you have is, so let's go to the minimizer. You have this gradient of u to the power 2 plus, what you can do is you put u to the power alpha here. Okay, that's positive part. So u is not negative, assume u is not negative. If you put, when you're doing in B1, so for alpha is 0, for alpha is 1, this gives the obstacle problem. For alpha is 0 in the limit, this gives a Bernoulli problem. Because it becomes the characteristic function. When alpha is 0, it becomes this. And this one becomes u to the power 1 here. Well, with the 2 ahead, that doesn't really matter. This is what it becomes. In our problem, we had a 2 here. I don't have a 2 here. And then for alpha in between, alpha can be, of course, you can choose alpha whatever you want to, as long as this is meaningful. And then for a different alpha, yes, different free boundary problems. So for different alpha, you get different free boundary problems. And these are all sort of partly studied, partly open. Then when you go for alpha larger than 1, for instance, this becomes a little bit, for alpha larger than 1, this becomes a little bit of trouble. It is a little bit more, it's more difficult. It's alpha in some range. Reasonable range. So these are things that people are studying nowadays, one thing that we have also been doing is the system case for this calculator. So Bernoulli again, system case. Yes, when is non-negative. The vector is all components are non-negative. So this is something that that has been. That's an interesting story behind this. So this is a paper of 81 of Hans Wilhelm Alt and Louis Schiaparelli. And then in 82 or 3 there's another paper, and then a few, I wouldn't say a few, I would say probably a bunch of papers came out. And then, so the regularity theory for this, existence regularity, of course regularity of free boundary, is very delicate. It's much more delicate than what I've been telling you. So it's much harder than the obstacle problem. So what happened that then nobody worked on this besides the specific versions that are going around with similar perturbation and other things. So it took, what's that going to be, 80 to 2016 or something like that, or 2017, so it took, what's going to be 30-something years? So it took 30-something years, and then in this summer, was it this summer, last summer? Maybe this summer, then we came up with working for the system. So we put the paper, finished the paper in August. After like 10 days, a similar paper came up. And after another 2 weeks, another paper came up with similar results. So you see, after 30-something years, nobody did anything, and all of a sudden, 3 groups of people were working on this at the same, within a week. Within 10 days they came up. So this was quite interesting. But anyway, this happens. I think that one can always say, that this is a very good company. Some other people are interested. So this we have now worked out, and we have proven regularity theory for these problems. So we went through. So what we did, we went through the machinery that already exists. We can do that most of the way, and then we can come down to the PDE. That because if you make a variation of this, if you just try to make a variation of this, the variation of this will be 0 when u is positive, because it's just constant. There is no variation. So vector u is positive. So here is, let's say, the vector u is positive. Here the vector u is 0. If you make a variation here, you're just making variation of this. Variation of this is the Laplacian. Okay? I mean, if you take the derivative of this, if it gives you the Laplacian, variation of this will give you 0, because it's just constant. So it will be a harmonic function here. So each component here will be harmonic. And of course it's 0 here. So what happens is that you have a measure on the boundary, on the free boundary you have a measure. So you can write it as, you can actually write it, compute it, and it comes down to the vector u itself divided by u times characteristic function over the boundary of the vector is positive. So this is on the boundary, it's not on the domain. And then Hausdorff measures something like this, h minus 1. This is what you get. It's a matter of computation, it's technical computation, but this is what you get after computing, after making variation. This will be 0 inside, it's 0 here, it lives only on the boundary. And each component satisfies this. So if I write this as the function g of x, then classical theory of papers of Alt and Caffarelli tells us that if you have such a PDE, and if the free boundary is sort of preliminary flat, a little bit flat, and G is C alpha, then you're going to get that the free boundary is actually C1 alpha. That's a heavy machinery, actually. To get through that, it might take good students several months to go through that machinery. But that works, and you can actually prove the free boundary is C1 alpha. However, what we have is that this function u vector over u, we don't know what it is. We know it's Solver problem. We know it's Lipschitz. We don't know if on the boundary, what is the value for this on the boundary. Inside this analytic function, each component is analytic. So absolute value of u is going to be a smooth function, sort of. And then u divided u1 divided by this is also a smooth function inside. But on the boundary, I don't know. If I can prove that this function on the boundary is C alpha, then I can use classical theory. So that was the idea, to reduce this to scalar case. And we did that by using a little bit different tools, proving that when you have flatness, the boundary is sort of smooth, that you can use some other tools. Like you can prove it's non-tangentially accessible. It's called non-tangentially accessible means that you can go in sort of directions like this and you can still reach the boundary. You don't need to go like this. You can still go, it might be wiggling, but you can actually reach the boundary for corkscrew conditions, etc. So those conditions actually will give us that boundary Harnack that I told you about. I didn't do it, but I told you about. The boundary Harnack can be applied to non-tangentially accessible domains. And then all you need to do is a trick that this you can actually rewrite it. You can actually rewrite it and apply your boundary Harnack technique to this. And then you get actually that this is going to be C alpha according to classical result. If it's C alpha, then you can apply all the result of Caffarelli. So this is behind. I think probably I should have put my slides here and show you, but it's a little technical, a little bit away from what we have been talking about here, so I don't want to maybe expand it too much. So that's another thing. I'm thinking about what else would be connected to this. Do we have questions? That freshes my mind.
Can you speak about quadrature?
You like that? Yeah.
Yes. Yeah. I think they would also like it, maybe at least the introduction part.
Yeah, I don't see how relevant that would be, but very glad to
You
do it.
want something else? Then?
I'm just trying to keep within a. But I can talk about it.
What about this boundary Harnack inequality?
Oh, that's
Is it sketch that or it's
that's fun.
not for the system, for the previous in the previous lecture you said.
Yeah, but that was also tough. I don't think I can do that on top of my head. To have slides.
No.
It would take a few hours to do it completely. Because I have to go all the way. I have to sort of go into labyrinths to find the proofs at the spot. And that would take a little time. There's actually a nice proof of bound Harnack by probability. Should probably look at that if you're interested in the probability way. But No, I don't remember complete proofs, so that would take some time. Trying to think of what I'm trying to not go too much away from the topic. The partial domain is a little bit maybe away, but still. Okay, then let me I was going to let go connect to a few things. Maybe I can start with partial domain and connect the problem also. Some connections. Good. Oh my God, connections. Okay, and let's say partial domain theory. Quadrature domains. So partial domains are domains that meet the mean value property. So recall the mean value property over a ball, radius r, center z. This is going to go the volume times hz. Okay? This is a quadrature domain. If you have this mean value property, well, you have it, of course, for balls of radius, of fixed radius, and functions that are harmonic and integrable, you can always get this. So for integrable harmonic functions, you always get this. So this somehow can be extended to more general concepts to extend it. And this was of interest for mostly people in geophysics. So they have this interest, and had to do with, they call it gravity-equivalent bodies. So they want to see that if they have this gravitational field, if they have gravitational field of an